We use equations when we want to describe the situation where two quantities are exactly equal to one another. Often, however, in mathematics and in applications, we want to describe that one quantity is greater than another or less than another. And we call these kinds of relations inequalities. So we're familiar with them, but we want to make sure that we have a very precise definition of what it means. So we'll say that A is less than B to mean, in words, A is less than B. And precisely what this means is that A is to the left of B on a number line. A number line is going to be absolutely essential to understanding inequalities and to describing their solutions when we get to it. And so the inequality A less than B always means that A is to the left of B on the number line. Now this works intuitively when we're working with positive numbers, but when we're working with negative numbers, we can sometimes get things that look a little bit strange at first glance. But before we get into examples, let's finish up. We'll say that A is greater than B to mean that A is to the right of B on a number line. And we'll say that A is less than or equal to B to mean that one of two things is true. To mean that A is less than B or A is equal to B. And A is greater than or equal to B to mean that A is greater than B or A is equal to B. So, for a few examples, we can get a number line here and keep track of things. So, if we want to look at 3 and 5 and say, well, how do they compare? We can graph them out on the number line and see that 3 is to the left of 5. And so we could write that 3 is less than 5 or 3 is less than or equal to 5. Both of these statements are true. Now, if we want to compare -7 and -3, let's look at these 2 points on the number line. And we can see that -7 is to the left of -3. That means that -7 is less than -3. Also, we'll say that -7 is less than or equal to -3. Whether we want the strict less than or the weak less than or equal to depends on the context and depends on the kind of problem that we're working with. So, in order to describe these, we will call the less than and greater than inequalities the strict inequalities, because to say that A is less than B means that A is actually less than B. It can't be equal, it has to actually be less. And then less than or equal to and greater than or equal to are called the weak inequalities, because to say that A is less than or equal to B, well, isn't as strict. A might be less than B or A might be less than or equal to B. So for instance, we have that 7 is less than or equal to 7. But of course, 7 is not less than 7. So we have that the weak inequalities hold sometimes when the strict inequalities don't. Now, what we really need to know in order to work with inequalities and to talk about their solutions is to know what happens to inequalities when we start doing algebraic operations to both sides, adding, subtracting, multiplying, or dividing, just as we did with equalities. In fact, we're going to use many of the same techniques that we used for equalities to work with inequalities. So, we have the following facts that we're going to use when working with inequalities. So we have addition. If A is less than B, and C is any real number, then A plus C is less than B plus C. A nice intuitive way of thinking about inequalities is often to think of a scale. If I've got a scale here and I'm measuring two quantities A and B, then to say that A is less than B means that there's less weight on the side with A than there is with B. And now if I take any number, any other quantity, and I add the same quantity to both sides of this scale, that's not going to change which side of the scale is heavier. The right side with B is still going to be heavier. Another way of thinking about this is that adding C to the two sides of this inequality just means comparing two numbers that are shifted by C on the number line. And if I've got A and B, and since A is less than B, I know that A is to the left of B on the number line, and then I add C to both of those, then the distance that I've moved to the right for A is the same as the distance that I've moved to the right for B, and so A plus C is still going to be less than B plus C because A plus C is still to the left of B plus C on the number line. So this handles addition, and it of course also handles subtraction, because subtracting a number is the same as adding the negative. So we can in fact say that A plus or minus C is less than B plus or minus C. Actually, let me make that slightly more precise. So we have that A plus C is less than B plus C, and we have that A minus C is less than B minus C. We can add or subtract anything we like to both sides of an inequality, and the inequality remains true. Now, multiplication works similarly, but here's where we have to be careful. Most of the time when we are going to solve inequalities, we're going to use all the same techniques that we use for solving equations. The difference is that we have to be very careful when we multiply or divide by a negative number. So let's see how this fact goes. If A is less than B and C is greater than or equal to, greater than 0, then A times C is less than B times C. However, if A is less than B and C is less than 0, then A times C is greater than B times C. Note the difference here. In both of our conclusions, for the positive and the negative case, we have A times C on the left, B times C on the right, but the difference is that the direction of the inequality has changed. This obviously isn't a possibility when you're working with equalities, because equality is what we call symmetric. Saying that A equals B is the same as saying B equals A. But the inequalities are non-symmetric. A less than B means something very different than B is less than A. And so we have to pay close attention to what happens to the inequalities. So the point here is that if we multiply both sides of an equation by a negative number, or divide both sides of an equation by a negative number, we have to change the direction of the inequality. If we do that, then we are safe. Now, we won't go through a whole proof of this, but we can do a quick example to see that this is true. So we have that 2 is less than 3. Now, if I multiply -5 on both sides, let's see what I get. 2 times -5 is equal to -10. 3 times -5 is -15. And if we look at a number line, 0, -10, -15, we see that -15 is to the left of -10, which means that 3 times -5 is less than 2 times -5. So by multiplying both sides of our inequality, 2 is less than 3, by a negative number, we get a new inequality where the direction of the inequality has been switched. This is a very, very important fact to remember. It's different than what we get when we're working with equalities, and so you want to pay close attention to how we work with this. So let's start talking about solutions to inequalities and how we can find them and express them. So we might look at inequalities of the form, let's say 2 plus x is greater than or equal to 3x minus 1. And this inequality is going to be sometimes true and sometimes false. So this will be true or false depending on the values, or on the value of x. The solution to an inequality is similar to the solution to an equation. The solution to an inequality is the set of all values of the variable making the inequality true. Now, the big difference between equations and inequalities is the following. With equations, we typically have only a few solutions, often just one if we're dealing with linear equations. When we're dealing with quadratic equations, we can have up to 2, and so forth and so on. But we generally have just a small collection of solutions to equations. And that's because saying that two expressions are equal to one another, have exactly the same value, is a very strong statement. It's hard to make happen. Inequalities, on the other hand, are weaker. They're satisfied a lot more. And so when you are working with inequalities, it is almost always the case that your solution contains infinitely many numbers, which will typically be expressed using interval notation, which we'll look at here in a moment. For this example, notice that if x is equal to 0, then our inequality becomes 2 plus 0 is greater than or equal to 3 plus 0 minus 1. And if we simplify both sides, that's the same as saying 2 is greater than or equal to -1. And this is true. So that means that 0 is a solution to the inequality. However, if x is equal to 2, then we'd get 2 plus 2 is greater than or equal to 3 times 2 minus 1, which simplifies down to 4 is greater than or equal to 5, which is not true. So that means that 2 is not a solution to the inequality. So the question becomes, how do we find the solution to an inequality, and then how do we express it? The answer is going to be that we're going to follow the same techniques that we used for equations typically. And when we're dealing with a linear inequality like this, an inequality that involves only linear expressions on the two sides of it, we can solve for the variable. So, for linear equations, we solve by isolating the variable. So let's look at that with this example. So we have 2 plus x is greater than or equal to 3x minus 1. And what we want to do is we want to get x by itself on one side of this inequality. And once we do that, we will have an inequality which will be much easier to describe the solutions to. So we're going to want to get all the x's on one side and all the constant terms on the other. As with equations, it doesn't really matter which way you choose, so I'm going to elect to subtract 3x from both sides to eliminate the variable term on the right-hand side. And that'll give 2 minus 2x on the left-hand side and a negative 1 on the right-hand side. Now, I've added or subtracted something here, which means that the direction of the inequality doesn't change. So it was a greater than or equal to before. I've added or subtracted something to both sides of the equation, so it's a greater than or equal to afterwards. The direction of the inequality never changes when you're just adding or subtracting something. Now, similarly, we can subtract 2 from both sides in order to get the constant term out of the left-hand side of the equation, and we get negative 2x is greater than or equal to negative 3. But now we need to get x by itself. So we're going to divide both sides by negative 2. And this is where we have to be careful. Whenever you multiply or divide by anything when working with an inequality, you need to check to see, did I multiply or divide both sides of my inequality by a negative number or a positive number? If you multiplied or divided both sides by a positive number, then the direction of the inequality stays the same. If, however, you multiplied or divided by a negative number, you have to switch the direction of the inequality. So, in this case, we've divided both sides by negative 2 because we want to get x by itself. But that means that we have to change the direction of the inequality. We divided by a negative number, which means that the inequality here changes its direction. Instead of being greater than or equal to, it's going to switch and become less than or equal to. Now, notice that the fact that we've got a negative 3 on the other side doesn't make any difference at all. Whether there are negative numbers in your inequality doesn't matter at all unless you're multiplying or dividing by it. So, when you're dividing by a negative number, when that's the thing you're doing to both sides of the equation, or multiplying by a negative number, you have to switch the direction of the inequality. So in this case, we can do that. On the right-hand side, we have negative 3 over negative 2. The negatives cancel, because a negative divided by negative is a positive, and we get the inequality x is less than or equal to 3/2. Now, the point is that this inequality has the same solution set as the original inequality. The difference is that the inequality x is less than or equal to 3/2 is really easy to understand because we've just got x by itself there, and so we can just say, well, is that number less than or equal to 3/2? And if so, then it's a solution to the inequality. So from this we can say that lots of numbers are solutions. So we have that 0 is a solution, which we found before. We've got that 1 is a solution because 1 is less than 3/2. We have that -5 is a solution because -5 is less than or equal to 3/2. We have that 3/2 is a solution because it's less than or equal to 3/2 because it happens to be 3/2. And of course, a whole bunch more. We're never going to be able to describe all of the solutions by listing them out because there are just infinitely many of them. There are there's one graphical way that we have of describing solutions, which is often good for intuition, for making things make sense intuitively. So what we can do is we can go to our number line and we're going to shade all the numbers that are solutions to our original equation. But that means we're going to shade all of the numbers that are less than or equal to 3/2. So for this, of course, we need to know where 3/2 is, and it's right there. It's 1 and 1/2. And then we're going to include all the numbers to the left of 3/2 because our solution is the set of all numbers that are less than or equal to 3/2. So we can shade all the numbers in the number line to the left of 3/2. And now from here, we want to put a symbol on the 3/2 that will be determined by whether this is a strict or a weak inequality. So in this case, we have a weak inequality, meaning that the solution includes all numbers that are less than 3/2, but also 3/2 itself. In that case, we're going to use the following notation where we put a square bracket on the number line pointing in the direction of our solution set. And the reason why we include this will become clear in a moment when we write down the interval notation. Now, another common way that people write this down visually would be to, again, use the shading here, or perhaps a line. And then when we get to 3/2, we'll use a solid dot. So let me point out right now that the solid dot is for a weak inequality, one that actually includes the endpoint, the 3/2. A strict inequality would use an open circle going to the left, indicating that our solution includes all the numbers up to that one, up to the 3/2, for instance, if this were a strict inequality, but not including it. And similarly, we have different notation on the number line. Instead of using the square bracket, which we use for the weak, for the strict, we would use a parenthesis. So these are the notations we would use on the right in the case that we were working with a strict inequality. We'll see an example of that later. So this is one way of writing down the solutions to an inequality. The other common way of writing down the solutions to the inequality are using interval notation. Interval notation will describe all the numbers in our shaded green region, and it's going to do that by describing the two endpoints of the region. An interval is a collection of numbers that all lie, the set of all numbers that lie between two endpoints here. So in our case up here, we can look at the interval of our green shaded region here, and let me start on the right-hand side of the notation. The right-hand side of the notation is similar to the notation that we used on the number line. It's going to use the number 3/2 with a square bracket. And this means that 3/2 is the right-hand boundary of our interval. So when we look at our interval, it's going to extend to the left and to the right, and whatever the right-hand boundary is for that set of numbers goes here in the second position of the interval notation. Now the left-hand boundary goes in the first position. Now in this problem, there is no number which is a left-hand boundary here. The numbers in our solution set include all numbers less than 3/2, which means that our set of solutions just keeps going to the left further and further and further and further and further, and there's no end to it. And so in that case, we have a symbol that we use, a shorthand that we use to describe the fact that this interval goes on forever to the left, and in that case, we use the symbol -infinity. So the symbol -infinity here means that the interval goes forever to the left. It's important to note that our use of infinity here does not imply that infinity is a number or that -infinity is a number. We're using -infinity here because our interval has gone all the way off to the left. If we had an interval that went all the way off to the right forever and ever, we would use positive infinity in the right-hand component of the interval notation for the right-hand boundary. But these infinities are not numbers. They are just symbols, and they just mean, they're just shorthand for this interval goes on forever in this direction. In particular, this means that infinities always get a parenthesis. So infinity and -infinity, they always get a parenthesis. And this is because the parenthesis in interval notation means that the number or the element that's on that side with that parenthesis don't get included, aren't part of the solution. And that's what we want to say here. -infinity is not a solution to this inequality because -infinity isn't even a number. It doesn't make sense to plug -infinity into the original inequality. It doesn't make it true or false. It doesn't make any sense at all. So -infinity isn't included in our solution. And so infinity and -infinity always get the parenthesis, even though no matter what, no matter whether we're dealing with weak or strict inequalities. So the interval solution for our inequality here is the interval from -infinity to 3/2. And we say that this interval is open on the left, or parenthesis on the left, and closed on the right, or with a bracket on the right, meaning that we are including 3/2 in our solution set. All right, let's do another example. Let's solve 3 times x plus 1 is greater than 2 times x plus 2 minus 4. So this is another linear inequality, and we know it's going to be linear because, well, we don't know yet. When we expand out both sides of our inequality, we'll see that it's linear. So let's do that. When you're solving an inequality where the two sides are complicated, they've got parentheses and they're not all simplified, the first step is always to simplify it, just like with equations. Most of this whole process is just like the process of solving equations. So we'll go ahead and simplify this a bit. The left-hand side becomes 3x plus 3. The right-hand side becomes 2x plus 4 minus 4. And then we can simplify things down even further. So we get 3x plus 3 is greater than 2x. So that worked out. We got to simplify the right-hand side a little bit. And so now we can try to solve for x. Now it would be a little bit simpler to solve for x on the right-hand side because the right-hand side doesn't have any constant terms. So let's go ahead and do that. So we'll subtract 3x from both sides. And we'll get 3 is greater than negative x. Now we're going to divide both sides by negative 1. Now 3 divided by negative 1 is negative 3. Negative x divided by negative 1 is x. And because we divided by a negative number, we need to switch the direction of the inequality. So the inequality before said greater than, and the inequality after will say less than. And we switched because we divided by a negative number. So we get negative 3 is less than x, or x is greater than negative 3. A lot of times we may find that it's more intuitive or more convenient to write an inequality the other way round. So instead of writing the negative 3 on the left and the x on the right, we might want to write the x on the left and negative 3 on the right. You just have to make sure that your inequality keeps pointing in the right direction. So negative 3 being less than x is the same thing as saying that x is greater than negative 3. So we have that our solution set is the set of all x's where x is greater than negative 3. So let's go to our number line. So we want to note where our boundary is. Our boundary in this case is negative 3. And now we need to know which way we're going. We are asking for all the numbers x where x is greater than negative 3, which means we want all the numbers that sit to the right of negative 3 on the number line. So that takes care of part of our solution. So now when we get to negative 3, we have to ask, do we put a parenthesis or a bracket? And for that, we ask the question, is negative 3 a solution to the inequality? If we plug negative 3 into the equation, if we plug negative 3 in for x, would we get a true statement? And the answer is clearly no. Negative 3 is not greater than negative 3, and that means that negative 3 is not in the solution. We indicate that by using a parenthesis, or other texts, other classes might use the open circle to indicate that the solution includes all numbers bigger than negative 3. So it includes negative 2.9, negative 2.999, negative 2.99999999999, but it doesn't include negative 3. So our solution is all numbers greater than negative 3. We can sketch the solution on the number line like this, and then in interval notation, we would write it as follows. Now, the way I like to think about interval notation is the way that I mentioned before. I ask, what's the left boundary and what's the right boundary? What's the limit on how far to the left x can be? What's the limit on how small x can be to be a solution here? And what's the limit on how big x can be to be a solution here? Well, as long as you've graphed out the solution on a number line, this is fairly straightforward. We ask, what's the limit on how small x can be? What's the lower boundary on how small x can be? And in this case, it's -3. That's the limit on how small x can be, and it gets a parenthesis. It gets a parenthesis because we don't include -3. Our interval of solutions is going to start at -3, but not including it. It's going to include all numbers bigger than -3, but not actually -3. And so that's why -3 will get a parenthesis in this example. And on the right-hand side, how big can it get? Well, it can get as big as it likes. The solution set includes all numbers bigger than -3, so in particular, it has no upper limit. So our interval is going to be from -3 to infinity, because the interval has no boundary on the right, no upper boundary, and infinities always get parentheses, because infinity is not a number, and so infinity can't be part of your solution. So our solution to this inequality is the set of all numbers from -3 to infinity. That's the way that you solve inequalities that are linear inequalities that are simple. One thing that we also run into is what are called compound inequalities. Sometimes what you care about is not one quantity being greater than another, exactly, but that one quantity sits between two other ones. So let's think about how we would write down the following. Let's see, how would we express the statement x is strictly between 1 and 4. So we can look at our number line and try and get some insight there. So we're trying to describe the situation where x, the number x, has to be strictly between 1 and 4. So it has to do something like this. And so the question is, how can we express that using inequalities? Well, we can't do it using just a single inequality, because a single inequality just says that one quantity is bigger than another one. It doesn't say it lies between. But we can do it by combining two inequalities together. So we can say that x is strictly between 1 and 4 by saying that x is greater than 1 and less than 4 simultaneously. So notice what happens when we do that. We're taking a solution set that looks like this. The red one is the set of all numbers that are greater than 1. And then the blue will be the set of all numbers that are less than 4. And what we're doing here is we're finding their overlap. So what we're looking at when we want to describe x being between 1 and 4 is the overlap between the solutions to x is less than 4 and the inequality x is greater than 1. So we can express this situation by saying that x is greater than 1 and x is less than 4. This is what's known as a compound inequality. It's really more than one inequality that all have to be true at the same time. And compound inequalities will typically have solutions, or I should say often have solutions, that are intervals that don't go off infinitely in either directions, but often they will also. Now, many compound inequalities can be simplified. We can also express this as the following. X lies between 1 and 4, or in other words, 1 is less than x, and x is less than 4. So this is just another way of saying 1 is less than x, and x is less than 4. So this type of compound inequality is very common to run into, and we can handle it one of a couple of ways. The one way is to take a compound inequality that we want to solve and to break it up into its two component inequalities and solve each of those and bring them back together. That we will have to do some of the time. But much of the time we can actually solve both of them at once using our techniques of solving inequalities and equations. So let's talk about solving compound inequalities. So one strategy that we usually try to do first is to isolate x by itself in the middle of the inequality, and we're going to do this by adding and multiplying to all three sides of the inequality, the compound inequality. So let's see an example here. Let's say that we wanted to find the solutions to the following inequality. Negative 2 is less than or equal to 4x plus 6, which is less than or equal to 10. What we can do is to get equivalent compound inequalities that have the same solution set by adding and subtracting the same thing to all parts of this inequality at once. So let's see how that goes here, probably best seen with an example. I want to get x by itself in the middle. Now, there's currently only one x term and it's sitting in the middle. That's good. And so what we can do is we can try to get x by itself. And I'd start here by subtracting 6 from the middle expression. Now, to do that, to balance that out, I also have to subtract 6 from all the other parts of the inequality. So in a compound inequality like this, you have what I like to call 3 sides to it: the left side, the middle side, and the right side. And so if we subtract 6 from the middle side, we also have to subtract 6 from the left side and the right side together. So we get that negative 8 is less than 4x, which is less than or equal to 4. And now we can divide both sides, or not both sides, all 3 sides by 4. Now, every time you multiply or divide, you have to have a warning light go on in your head and say, am I multiplying or dividing by a negative number? If so, I need to change the directions of all of my inequalities. So in this situation, if we were multiplying or dividing by a negative number, we would need to change the direction of every single one of the inequalities involved. In this case, however, I'm dividing by a positive number, and so all the inequalities keep their same direction. So negative 8 divided by 4 is negative 2, 4x divided by 4 is x, we get 1 on the right. And so our conclusion here is that x has to be greater than -2 and less than or equal to -1. So let's sketch this out on a number line, and let's give our answer in interval notation as well. So 0, 1, -2 over here. So first of all, we want to include all numbers that are greater than -2 and less than 1. So we're certainly going to include all these numbers here. And now for each of our endpoints, we ask, would putting that endpoint into our compound inequality give us a true statement or not? So if we plug -2 in to our inequality, our compound inequality, we get something that is false, because 2 is not less than -2. So that means that -2 is not in the solution, which means that when we sketch out our solution on our number line, we're going to use a parenthesis on -2. On the other hand, if we plug 1 in, we would get -2 is less than 1 is less than or equal to 1, and this is a true statement. -2 is less than 1, and 1 is less than or equal to 1. So that means that we'll put a bracket here at 1, because 1 is a solution. So that's what our solution would look like graphed out on a number line. And the interval notation will look like the following. We want to look at the left boundary and the right boundary. Basically, what's the minimum value x is allowed to be, what's the maximum value x is allowed to be. And going from the number line, or just actually looking at the inequality we got down here, we can say, well, the boundary on how small x can be is -2. That's the limit. X always has to be bigger than -2. So -2 is the number that controls how small x can be, how negative it can be. And then we ask, all right, what's the boundary on the right? What controls how big x can be? And the number on the right that controls that is 1. So the two numbers that come from your compound inequality show up in your interval notation. Now, one thing to note here is that interval notation always reads from left to right with increasing numbers. So it has to read as -2, 1. It'll never read as 1, -2, because interval notation always only includes increasing numbers. The last thing we need to finish off the interval notation is to say what kind of parenthesis or square brackets do we have on the two sides. So the same argument, the same thought process that we used for the number line above applies here as well. -2 is not a solution to this inequality. Therefore, it gets a parenthesis. 1, on the other hand, is a solution to this inequality, so it gets a bracket. And so we get this interval here. Now, intervals could have parentheses on both sides, parentheses or brackets on both sides. They could have a mix like we see here. The only thing that is absolutely always going to be true is that when infinity shows up, it always gets a parenthesis. So this is how we can solve some kinds of compound inequalities, when we can isolate x by itself on one side, or rather on the middle side. Some types of compound inequalities don't submit to this, however. Let's look at the following. Let's solve the inequality 2x plus 1 is less than or equal to x plus 7, which is less than or equal to 4x minus 3. Well, in this case, if you try to get all the x's in the middle, it doesn't work. So, for instance, if you tried to, let's say, subtract 2x to get rid of the x on the left side, you get 1 is less than or equal to negative x plus 7, which is less than or equal to 2x minus 3. And you've gotten rid of the x on the left, but you haven't gotten rid of it on the right. And now, if we try to get rid of the one on the right, we'd subtract 2x, but we have to subtract 2x from all three sides. And so we'd get negative 2x plus 1 is less than or equal to negative 3x plus 7, which is less than or equal to negative 3. And we're stuck, because if we keep going back and forth, back and forth, back and forth like this, we're never going to be able to get just a single x in the middle side, and so we're not going to be able to solve for x the way we did before. That's unfortunate, and it means that we're going to have to work a little bit harder in order to get our answer, but we can still do it. So let's go ahead and get rid of all this, and let's see how we actually do it. So the other technique that we have is to split up the compound inequality. So remember that every compound inequality is just a shorthand for two separate inequalities. So we've got 2x plus 1 is less than or equal to x plus 7. So we have 2x plus 1 is less than or equal to x plus 7. And then we have that x plus 7 is less than or equal to 4x minus 3. And it's important that we make note that the word combining them, the logical operator combining them, is and. Both of these inequalities have to be true at the same time in order for a number x to be a solution to this compound inequality. Notice that this is different from, say, when we were solving equations, solving quadratic equations by factoring. There we had ors showing up because the zero product rule gives us an or statement. This is an and statement, and we want to be very clear about those. So now we can solve each one of these. We can solve 2x plus 1 is less than or equal to x plus 7. We can get the x's on one side, subtract x from both sides, get 2x plus 1 is less than or equal to 7, subtract 1 from both sides, get 2x is less than or equal to 6, and then divide both sides by 2. We check to say, oh, hey, did we multiply or divide by a negative number? We didn't. It was a positive number, so the inequality stays the same. So the first inequality in our compound inequality became x is less than or equal to 3. So now let's go to the other one. Again, we'll try and get x by itself. I'll go ahead and subtract 4x from both sides to get negative 3x plus 7 on the left and negative 3 on the right. We'll subtract 7 from both sides to get negative 3x is less than or equal to negative 10. And then we'll divide both sides by negative 3. But here's where we have to be careful, because we just divided by a negative number. So that means that the inequality that we have here, the less than or equal to, has to flip and has to become greater than or equal to. And so we get that x is greater than or equal to 10 thirds. And we have an and argument combining them. So for our compound inequality, what we wound up with at the end is that x is less than or equal to 3 and x is greater than or equal to 10 thirds. Now in this case, we were able to combine these together. We can flip the second inequality here to say that 10/3 is less than or equal to x. And now if we combine these two together, we can write down a new compound inequality. We can write 10/3 is less than or equal to x, and x is less than or equal to 3. And that gives us a compound inequality of the solution of the same kind that we had before. Now, we can sketch out the solution again, or we can jump straight to the solution in interval notation, depending on what the problem was asking for us. So in this case, x is going to have to be between 10/3 and 3, and both of those are solutions to the inequality. And we can tell that by the fact that we've got a less than or equal to, a weak inequality on both of those sides. So this is one thing that we can do in order to solve compound inequality. Now, not all compound inequalities are going to work out quite this nicely. Let's look at another one. So let's solve x minus 1 is less than or equal to 2x plus 3, which is less than or equal to 6x minus 1. Let's work this out the same way. Again, we're not going to be able to solve for x in the middle, so we're going to split it up. So this becomes x minus 1 is less than or equal to 2x plus 3, and 2x plus 3 is less than or equal to 6x minus 1. Now, solving for x, I can subtract x from both sides here, get negative 1 is less than or equal to x plus 3. And subtract 3 from both sides to get negative 4 is less than or equal to x. And then on the right-hand side, we can subtract 2x from both sides to get 3 is less than or equal to 4x minus 1. Add 1 to both sides to get 4 is less than or equal to 4x. And then divide both sides by 4, again checking to say, all right, do we need to change the direction of the inequality? We don't, because we're dividing by a positive number, and so we get 1 is less than or equal to x. So our solution, or getting close to our solution now, is negative 4 is less than or equal to x, and 1 is less than or equal to x. Now these don't combine into a compound inequality the way the previous answer did, because both of these inequalities are going basically the same direction with respect to x. Both of them are saying that x has to be bigger than some number. So let's look at, let's interpret this in terms of the number line. This is a good way of understanding what's going on. In order to graph out the final solution, let's graph out each one of these inequalities individually. So let me use the red color for the inequality x is greater than or equal to negative 4, or negative 4 is greater than or equal to x. That's going to be an inequality whose solution looks like this. So here's x is greater than or equal to negative 4, which is the red inequality that we had below. Now the blue inequality says x is greater than or equal to 1. So that's going to, we can write that down like that. X is greater than or equal to 1. And our solution is going to be the set of all numbers which satisfy both of these conditions at the same time. So for instance, the number 0 satisfies the red inequality, x is greater than or equal to -4, but doesn't satisfy the blue inequality of x is greater than or equal to 1. And so it's not a solution to the whole compound inequality. The only numbers that satisfy the compound inequality are the places on the number line where both inequalities are true at the same time. In other words, they're overlap. So what we're going to do is we're going to find the overlap of the two solutions to the component inequalities in the compound inequality. And in this case, you can see that the overlap is, in fact, the same as the solution to the blue inequality, because the solution to the blue inequality sits inside the solution to the red one. So in our case, our solution is going to be the set of all numbers from 1 to infinity, because that's where we get the overlap of the red inequality and the blue inequality. That's where both of the inequalities in the original statement are true at the same time.